Thanks for watching Physics 1. Welcome. I'm your host, Dr. Wisby, streaming to you tonight from the Carina Nebula. This is a nebula, or a star-forming region, about 8,500 light years from Earth. It's part of the Carina constellation, which was originally part of the Argo Norvis, which is Jason's ship. And the Carina constellation is located in the southern hemisphere. It was split into 3 different constellations in the 1700s because there were so many stars that were detected by astronomers at that time. In this picture, there is a star-forming region with over 14,000 stars in this particular region. So this is a very interesting nebula. You can find this in many other images on the Hubble site website. Today I'd like to talk to you about thermodynamics. That's what this chapter is all about, and we'll also review for the test. So, when we talk about thermodynamics, I always like to wear my favorite zombie t-shirt. Warning, if zombies are chasing us, I'm tripping you. Yes, that's true. And I'd like to talk about why the first law of thermodynamics prevents zombies from happening. Now, a lot of people think that a zombie apocalypse would be bad, but I like to think of it as more of a solution to our energy crisis. You see, we could solve global warming if the zombie apocalypse were real. And what I mean by that is, if zombies were real, we could, based on what we see in the movies, zombies can basically run forever, and they don't need to eat. Now, this violates everything that we've been learning about energy, because we know that it takes energy to move. But with zombies, all you need to do is show them a picture of someone with brains, and the zombies will chase them forever. So, what that means is we could take zombies, we could put them on treadmills, show them pictures of people with brains, and they would just keep running. They could generate an infinite amount of energy. We could use those treadmills to create electricity, and we would get an infinite amount of energy. That means that we would be creating energy out of nothing. So that violates the first law of thermodynamics, which is also known as conservation of energy. It states that energy can neither be created or destroyed. Energy can only be transferred or changed from one form to another. So, for example, turning on a light would seem to produce energy. However, it is electrical energy that is converted. So, when you turn on your light, you're getting energy from that coal-fired power plant, okay? But with zombies, if they don't need to eat, now maybe the zombie would wear out after a couple months, but they don't seem to need any source of fuel, okay? And since we're talking about thermodynamics, there would also be a problem with entropy, because we know that entropy is real, but zombies would seem to violate entropy as well, because if a person is dead, their body reaches equilibrium. There are no chemical processes going on, and so that means that they are in the highest state of entropy, meaning they can't go to a higher level of entropy. And so that means that as they were expending all of this energy, the entropy would be going up and up and up in the world. As they start producing all this energy, entropy would be increasing. Maybe that wouldn't be such a big deal, but they would no longer be at equilibrium. So, or they would be at equilibrium, but they would seem to be able to generate entropy out of nothing. Now let's think about if we put a zombie on a treadmill in an isolated room. That means that over time, the entropy of this system would go up and up and up. It would never ever reach equilibrium. And if you could never reach equilibrium, that means that entropy in our universe would start spiraling out of control, maybe. I don't really know what the consequences are of that. But before we get too far into why zombies would violate the second law of thermodynamics, let's talk about what the first and second law are. What do they mean? So the first law says that if I have my cup of coffee here, it's hot. So I heated up the water, and over time, the energy in my coffee that kept the coffee hot is going to dissipate. It's going to go up into the air in the room, and it will be lost in the air. I won't be able to get it back. The energy wasn't destroyed, but it's simply converted into some other form of energy. My coffee has cooled, and it's no longer hot. But all of the energy is still around me. It's still in the room. It hasn't been destroyed. We haven't lost it in any way. Now, where did I get the energy to heat this cup of coffee? Maybe coal, maybe a nuclear power plant. But that was energy that was trapped in some form that was there. And when I burned the coal, I released that energy to do mechanical work. That mechanical work created electricity, and then I used that electricity to create heat to raise the temperature of my coffee. So I transferred energy into my coffee. I gave it thermal energy, which is a macroscopic property. You can't give atoms really thermal energy. Not the way that you can a microscopic object. Because when my coffee gets hot, that means all of the water molecules in there are vibrating. So they're moving around, they're very hot, and they are in a state of excitation. Now, over time, they start to cool off. They're not moving as quickly, and all of that energy goes off into the room. Now, why do I have this giant hammer on my screen? The second law of thermodynamics says that some processes in our universe are not reversible. You might ask, well, why couldn't all of this thermal energy suddenly that's out here in the universe, why couldn't it suddenly flow back into my coffee? And it appears from our observations that there is something that keeps things from going backwards. So you might think of this as maybe the second law of thermodynamics keeps the universe moving forward. Some things are not reversible, and we can't go backwards. So some people are doing research in quantum computing to understand what is fundamentally the second law of thermodynamics, and is this the reason why we're moving forward in time? Right? Now, what do I mean when I say some things are not reversible? I'm glad you asked. Some things are reversible, some things are not reversible. Let me get my inclined plane and to show you what this hammer is for in a minute. Alright, so here I've got an inclined plane, and I can push my plate up here, and I can let it go, and it will slide back down. This is a reversible process. I can do this as many times as I want, and it's totally reversible. So I can change it. Now the entropy is going up, okay? Because every time I do this, it does dissipate some heat into the system. Some of the air molecules get excited, and some of that chemical energy that I use to push it up is being dissipated. So there's some drag on my plate, very little, but there's also friction. I can feel it rubbing on the plastic. But just the plate here moving up, this is a reversible process. Other things are not reversible. For example, if I took my hammer here, let's put my plate here, and I take my plate right now is in a state of equilibrium. The plate is probably a thermal equilibrium with the rest of the room. It's a normal plate. But if I take my hammer, now we've done it. The entropy in my plate has increased. This is not a reversible process. So if I were to run the video backwards, which I might be able to do later, that process cannot be reversed. It can't be put back together. I can glue it back together, but it will never be as it was. And all of that energy, those bonds cannot go backwards. This plate wouldn't suddenly put itself back together if I put the hammer here and pulled it up. So it will not go back together. This process is not reversible, and things in our universe are on the macroscopic scale are also not reversible. So the entropy is going to increase until it reaches equilibrium. When a system is in equilibrium, this is the highest entropy. Now, eventually, our universe will reach a point where it will reach the heat death of the universe. So when this goes on, okay, then it's going to reach the heat death of the universe. This is the place that some of these early physicists theorized would happen to the universe ultimately. Basically, it means that no more mechanical work can be done because energy has completely spread out to a place where you can't do mechanical work anymore. This would be the highest level of entropy in our universe, and no more work can be done. So a process that required mechanical work could no longer be sustained because nothing that could raise the entropy of the universe would be done. Anytime you do mechanical work, that is going to raise the entropy of our universe. Now, what does that mean in terms of zombies? Well, zombies would always be able to increase entropy because they would not require any energy to. They wouldn't require any energy to do mechanical work. So, from the point of view of entropy, what that would mean is that we could avoid the thermal death of the universe. So maybe zombies could actually save the universe by preventing the heat death of the universe. You see, we could prevent this because if we had enough zombies, we could generate heat and we could keep doing these processes that would raise the entropy of our universe. So there would be no limit. We could always pump more energy, get more energy from the zombies, and we could keep doing mechanical work. And the entropy of our universe would keep going up and up. So maybe if there was a zombie apocalypse, this could actually solve our energy crisis and prevent us from reaching the heat death of the universe. But we know that these things aren't possible. Some things are reversible in time. And so zombies are not possible. So would that mean that maybe zombies could travel backwards in time? Well, that is a question for a different video. Thanks for watching. This has been Thermodynamics. Thanks for watching this video about the thermodynamics of...
Thank you, like and subscribe down below.